I want to quickly say that the only algebra I will be using is linear algebra. The reason for that is that this work was very much oriented towards software implementation, and as such, the algebra is only here as a method of conveying the message to the computer, to making it understandable by computers, and that's why only linear algebra is used. Okay, so let's begin. First, I'm going to talk a few words about MBQC, in case you are not familiar with that. So the standard model for quantum computation is the circuit model, where we would have qubits that run through quantum gates, and the quantum gates is what really does the quantum computation, right? And then in the end, we can either use the qubits for next computation, or we could measure them as in measure to get the final answer of the computation. However, there are different models. For example, MBQC, so measurement-based quantum computation, works differently. This is the notation that maybe you are not familiar if you have seen MBQC. I will be working with the notion of labeled open graphs, which I will explain in a minute. But what is MBQC? Well, MBQC is a model of quantum computation that is driven entirely by progressive single qubit adaptive measurements, where we prepare some highly entangled resource state. For example, it could be cluster state, but it can also be anything else. And then we measure qubits one by one, correcting the undesired outcomes, and in the end, this way we can move forward with the computation that we intend to perform. So usually the resource state that we are using is going to be some form of graph state. So what is a graph state? As a quick reminder, if we have a mathematical graph, we can always turn it into a graph state in the following way. For each vertex, we prepare a qubit in the state get plus, and then for each edge, we apply Ctrl Z gate between the two corresponding qubits. That's the way that we get a graph state. But the structure we will be working with is going to be a bit more complex. It's going to be an open graph. So an open graph is a triple that consists of graph, but also two designated set of vertices, input and output vertices. So the input vertices are going to be denoted with a box around them. So in this case, we have one input, which is qubit I, and this qubit is intended to be given by someone that wants to perform the computation, right? So we don't assume anything about its state at the beginning. And the output, the outputs are supposed to be qubits that are not measured as part of the computation. So in this case, we have two, that they will be represented with empty circles. So in this case, we have O1, O2 as outputs. And in terms of preparing a starting resource state, what we would do is we would still prepare a system on V qubits. Some of the qubits are inputs, so we don't prepare them again. Instead, we only prepare instead ket plus now non-inputs. And then again, we would apply Ctrl Z gate to the pairs of qubits that are connected by an edge. And what drives the measurement-based quantum computation forwards are, of course, the measurements. So what are the measurements that we are allowing here? We will be working with the model that allows three types of planar measurements corresponding to the Bloch sphere. Those are XY, YZ, and XZ planar measurements. And we will also treat intersections between those planes separately. Those give us poly measurements, so poly X, poly Y, and poly Z measurements. Based on that, we can define what we will call a measurement label, which is an assignment of measurement bases for each non-output. So each measured qubit, we are choosing one of those 6 possibilities of how we want to measure them. Something else that I want to point here is that exact measurement angles that would correspond to the planar measurements are irrelevant in our setting. So always we would have to specify at which angle we are measuring a qubit in a plane, but that won't be important in the model that we will soon look at of Polyflow. So let's look at now what is a labeled open graph. This is the structure that I will be using to fully denote the measurement-based quantum computation that one wants to perform. So a labeled open graph is a quadruple that consists of an open graph, so GIO is an open graph, and then a set of measurements, so measurement label, so a choice of measurement for each of the measured qubits. And this is the notion that I will be using to describe measurement-based quantum computation. Some initial works here would, for example, only use planar XY measurements and Z measurements on cluster states. That would be sufficient to get universal computation. But what I will be using is I'm allowing the 6 types of computation, and we are not only working with cluster states, we are working with arbitrary graphs as underlying the structure. Okay, so now I can discuss the most important part of the talk, and that is about determinism. So quantum measurements are non-deterministic. So just that we specify that we want to perform computation given by labeled open graph doesn't necessarily mean that we can actually do that in a deterministic way. Because whenever we are measuring something, we can get 2 outcomes. And out of those 2 outcomes, only one is the desired outcome. So if we get an undesired outcome, we must correct it. And what I mean by that, well, I think it's easiest if we look at an example. So we are back to this labeled open graph. We will use this labeled open graph as an example throughout the talk. Suppose that we get undesired outcome when measuring qubit I. So in terms of exact states, it means that the effect that we wanted to observe would be ket plus in plane xy at some angle, but we will get ket minus. And the 2 states, they are differing by Z byproduct. So that means that we got the outcome we didn't want, and it differs from what we wanted to obtain by Z byproduct. So we must be able to correct it in some way. And what we will be doing for corrections is completing the stabilizers of the graph state. So in this case, we can, for example, complete it to stabilizer given by qubit B. What exactly does it mean? It means that we can apply X gate to B and Z gate to its neighbors. So in this case, we would apply Z gate to EDO2. We don't apply it to I because we assume that on I we already have this byproduct that we want to get rid of. So if we do that, in this case, we would complete to a stabilizer, and because of that, we would not have to worry about the fact that we got undesired outcome, because we brought the state to one we would be in if we got the desired outcome. However, there is one more thing here that we must focus on, and that is in order to apply those gates to those 3 qubits EDO2, we must necessarily be able to apply that in, meaning that those qubits physically exist, for example. So, for example, they were not measured before. And because of that, I must be necessarily measured before BE and O2. However, note that we don't have to necessarily measure I before state D. So why is that? Well, qubit D is in the end measured in Z basis, poly Z basis. And applying a Z gate to something that is measured in Z basis would only affect the global phase. So because of that, we might as well just ignore the fact that it has to be applied. And because of that, we don't get a constraint that we must measure I necessarily before D. This is just an example of how we could correct one measurement outcome that is undesired. And the question arises, how can we formalize in general whether such corrections are possible? And it turns out that there is a known structure that tells us when we are able to correct by complementing to a stabilizer undesired outcomes, and that structure is known as polyflow, which I will discuss now. So what is polyflow? Well, polyflow is the structure that precisely corresponds to robustly deterministic or strong uniform stepwise deterministic computation that can be performed on a labeled open graph. Polyflow will precisely correspond to robustly deterministic computation. And itself, polyflow is defined as a pair of correction function and partial order. So the C here is the correction function, which to each non-output specifies sets of non-inputs that we would use for correction. So that specifies the stabilizer that we are trying to complement to for each measurement. And then the partial order is just the order in which we are supposed to measure non-outputs so that these corrections can actually happen. And that's all fine so far. There is just one problem. Well, it's of course not just any pair. They have to specify some conditions. But because we are working in a setting where we are allowing 6 different types of measurements, the amount of conditions that we have to consider quickly explodes. And what I mean by that is that the structure we get when trying to work out all the possible different applications of how a qubit can be used for correction and also what type of correction exactly it needs due to the byproduct, we just get a lot of different conditions that needs to be satisfied. And yeah, I'm not going to go through all of these conditions in detail because that would be pointless. There is just a lot of them. But maybe let's look at some categories of those conditions that we have. So we have some order restrictions that tell us in what order we can measure the qubits. We have some conditions that tell us how we need to correct planar measurements based on the byproduct that they are producing. The same for Pauli measurements. And then in practice, we also like to add, when working with flow structures, some extra conditions that are called focusing conditions. So in total, we just get a lot of different conditions that we need to satisfy in order to be able to say this computation given by labeled open graph can be done in a deterministic way. So I think it's easier if I just show you an example, but even the example I'm going to only brush on. So here we have the labeled open graph we saw previously, and then the polyflow as the structure that tells us how to do computation in a deterministic way is presented in the table. So for example, qubit I, if we measure it, we can complement to a stabilizer given by vertices BE01, which means that we would apply X gate to BE01 and Z gate to odd neighborhood, which in this case is IB01. But on I, we wouldn't apply the gate because that's where we would get byproduct. And the same can be done for all of different measured qubits. Again, this is only like giving you an overview, right? Each different measurements requires slightly different correction and can be used in a slightly different way for correction as well. If we were to do this computation this way, there is also some partial order involved in which we have to measure qubits. So in this case, we necessarily would have to measure A, I, and B before E. But other than that, we are free to measure vertices in any way we want. So moving on, let's also look at an example without flow that will maybe show this partial order a little bit more again. So in this case, we have one input, one output, 3 qubits in total. And in this case, we don't have flow, meaning that we cannot perform this computation in a robustly deterministic way. And why is that? Suppose that we measure qubit I, and we want to correct undesired outcome that might happen there. So we can either use qubit A or qubit O for stabilizer. The problem is that whichever we use, we always will get the constraint that I must be measured before A. So we will always have to apply something to A, which means that because of that, qubit I must be measured before A. But we can also look at qubit A, and in a similar way, we would obtain that it would be necessary to measure qubit A before qubit I. We would need to apply some gate to I in order to correct undesired outcome for qubit A. What it means overall is that there is just no order in which we can measure the vertices in order to perform this computation in a robustly deterministic way. So in this case, there is no flow for the reason that we wouldn't be able to construct a suitable partial order. Okay, so what are the applications of flow, that the structure that I showed you? The most important idea follows from the fact that this is precisely corresponding to robust determinism. So being able to perform computation in a robustly deterministic way requires existence of polyflow. And because of that, there are tools for MPQC. For example, graphics is a tool, software tool that will, because of that, look for flow as their way of going forward with computation in deterministic way. But those aren't the only applications of flow. For example, flow is used very extensively in circuit optimization and ZX calculus. So what is that? Well, circuit optimization is a question of, if we have computation given by a circuit, can we find a more efficient circuit? For example, there is a lot of research put into reducing number of T-gates, so T-count reduction. And it turns out that flow structures were used to get some state-of-the-art algorithms for reducing T-count. And they are using ZX calculus, so another topic that I won't go into. This is a graphical language for quantum computation. The idea there is that we need flow in order to be able to move back from diagram that we would have in ZX calculus to a circuit. So we only know how to do that efficiently if we have flow. So that is another way in which flows just appears as a necessary structure. And there are also other areas in which flow is applied. All of those are very much computation-based. So there is a blind quantum computation, for example. So this is a protocol for exchange of information in a way that wouldn't compromise privacy of the two parties. And there are now some protocols for blind quantum computation that are based around flow. The flow is also used in fault tolerance. Some topics such as lattice surgery have a structure known as polyfusion flow, which turns out to be very similar to flow. But those aren't the topics that we will focus on. We were just focusing on how to work with flow. So what are the issues with polyflow? First of all, the definition, as I showed you, is extremely long, right? All of those conditions, it's hard to work with them. And that is a problem, because if you want to show that something is polyflow, meaning you can perform computation in a deterministic way, you suddenly have to verify all of those conditions, which is just a very tedious process. Another problem with polyflow is that some of those applications that I told you about, like the T-count reduction, for example, they might have to find flow at some point. But flow finding algorithms, while they exist, so given label open graph, tell me what is the polyflow, they may exist, but they are slow. Right? They are slow because they run in time n to power 4, where n is number of vertices. This is just a lot of operations. It's very computationally expensive. So this work, what I will talk to you is I will show you how we can give matrix interpretation for the conditions of polyflow that simplifies the conditions, or just the overview of that. And I will also explain how, based on that, we can speed up the process of finding flow. And I will also look at some other possible applications. So algebraic interpretation, big word for what will be basically matrix multiplication and matrix inverse. So first of all, maybe what I mean by algebraic interpretation is just simplifying that set, that wall of conditions, to something that could be understood by computer and is just easier to work with overall. There was some initial work that showed how to do that if we have only xy measurements. But if we only have xy measurements, then we don't have that wall of conditions. We can drop most of them because the conditions just arise because of different types of measurements that we are allowing. I won't give, however, too many details about this algebraic interpretation, but what I mean is that we constructed some matrix that captures most of the conditions. I will show which conditions in a second, where this is just some easy or semi-easy way of filling the matrix of some given shape. dependent on different for different measurements in a different way in terms of rows. So I will only give one example of what would happen is that rows for y measured vertices we would fill via adjacency and putting one at the intersection of row and column for such measurement. And the idea here is that doing this, we will be able to recover many of the conditions by then looking for some matrix product. So going into details why we are doing things this way would require me again to spend a lot of time explaining different byproducts for each of the measurements. So that's not something I want to go with. I want to show you the overview. So let's look also at overview of correction matrix. What I mean by that is that if we have a labeled open graph and we have some candidate for correction function, so the specification of stabilizers to which we want to complete by products, then we can always encode such matrix, such correction function as a matrix in the following way, where we would say that columns are corresponding to those sets that specify the stabilizers. And as it turns out, if we do that, we are able to say that a necessary condition for something to give rise to flow eventually will be that the product M, so that flow demand matrix from earlier, from previous slide, times correction matrix must necessarily equal identity. So this is just a way of visualizing those wall of conditions in a slightly simpler terms by something that can also be easily understood by a computer. And those are the exact conditions that this condition MC equals identity corresponds to. So if we want MC to equal identity, it means that all of these conditions must be satisfied. That's the overview of why it would work. And here is the example, right? So if we multiply the two matrices we saw in previous slides, we indeed get identity. And from the fact that it must be identity, we would be able to recover all of those conditions that have to be specified, satisfied by the correction function. So we get most of the conditions. We don't get all of the conditions, and that's why there was also another matrix needed, which is what we call order demand matrix. This is another matrix that would arise in a similar fashion. We would again construct it in terms of rows. And I don't want to spend any time on this construction, just some construction exists that allows us to get to the following picture, or algebraic interpretation, as we call it in the paper, where first we saw that M times C must be equal identity, and now the condition is that N, so that order demand matrix times correction matrix must necessarily form a directed acyclic graph. And that is a graph that precisely gives us the partial order, from which we can recover the order in which we have to measure the qubits. And because of that, we can get the full theorem, which is that given a labeled open graph, if we say that M is flow demand matrix and N is order demand matrix, then a polyflow exists if and only if MC equals identity and NC is a DAG, where C is some correction matrix. So here is the full example. We saw all of those matrices except for the product NC. So product NC here would give us the way of regaining the information that I must be measured before E, A must be measured before E, and B must be measured before E, because that's where we would get ones in the matrix. So this is just a matrix visualization of the conditions for deterministic computation on labeled open graphs. Okay, so I've made on many occasions claims that this is easier. I probably didn't make a very good job of explaining why exactly I think it's easier. So maybe I will show you some applications of using this algebraic characterization. So first of all, we can speed up the problem of finding flow. I explained that this is important, for example, because of T-count optimization, or for circuit extraction from ZX calculus. This is just something that sometimes has to be done, that we have to find explicitly how the structure of flow looks like. So because of that, there was a lot of research to check whether we can do it in polynomial time. And yes, we can do it in polynomial time. It's already known. There were initial works in 2015 around that showed what can we do if we have only XY planar measurements. Then it was extended to all planes. Then another algorithm was done to capture all 6 types of measurements. But the problem is that all of those algorithms were having complexity O(n) to power 4 or worse. So they were quite slow. But thanks to this algebraic presentation of the conditions, we can do it faster. And what I mean by that, well, flow demand matrix has shape that is non-outputs by non-inputs. Doesn't exactly matter why. What matters is that this matrix is square when we will have equal number of inputs and outputs. And when the matrix is square, of course, if it has a right inverse, that right inverse is just its inverse in general. So if it exists, it's unique. And that gives rise to a very, very short algorithm for finding polyflow. So we can just compute flow demand matrix and order demand matrix, which are easy to construct. Then we can compute a unique inverse, or output it doesn't exist, so there cannot be flow. So you cannot perform computation in deterministic way. Then you can compute this another matrix product, and based on that, you can check if that's a directed acyclic graph, so whether we get something that gives rise to a valid partial order, in which we would measure the qubits. And if we don't get a directed acyclic graph, we again output that there is no flow. And finally, if we did, then we can output the correction matrix C and matrix of the induced order to tell us, well, that's the notion of polyflow in this case. This is the set of instructions to get robust determinism. And the complexity of such approach is just how fast we can do matrix inverse and matrix multiplication. So if we do something basic like Gaussian elimination, that gives complexity O(n) to power 3, which is already faster than what people were able to do before. But there are possibly some faster ways, like Strassen algorithm possibly can drop this complexity to drop the exponent to logarithm base 2 of 7 or something like that, so roughly 2.8. So what's very important also is that we were able to get lower bound that links matrix inverse to the problem of finding flow, and overall we can now claim that further speedups in the topic of finding polyflow will have to come necessarily from matrix inverse and matrix multiplication research rather than quantum side of research. Another application that I want to talk about is what if we don't know the measurement labels. So suppose that someone goes to the lab and they discover they can prepare some type of graph state where they can only, let's say, due to the time in which, due to the order in which the vertices are produced, they can only use some of the vertices as inputs, and only some of the vertices can remain unmeasured at the end. The question then is, can we do any interesting computation on such graph state? So the meaning of interesting computation is that we probably want that computation to be possible in a deterministic way, because if it's not possible in a deterministic way, then there's not really a reason to try to do that computation in practice. And that then translates to the question of whether can we choose some measurement labels that would result in polyflow. The question, can we efficiently find measurement labeling resulting in polyflow, is quite important because of that. Efficiently is the key word here, because we of course could just check all of different possible measurements, but that would be quite slow. There would be exponentially many of them. But if we only but if we actually want to look for efficient way of finding such measurement labels, the question is quite difficult. And it turns out that we actually can do that. So how can we do that? Well, the way that the solution that I found is quite boring in the sense that it only looks for poly X and poly Z measurements for a labeled open graph to decide existence of polyflow and hence deterministic computation. It turns out that that's sufficient in the way that if we cannot do computation with just poly X and Z, we cannot do with any of the measurements. So in that sense, it's sufficient to look for poly X and Z. But of course, that's also not very interesting in the sense that if we only have poly measurements, we are in the Clifford fragment, so that could be classically simulated. But how can we do that here? It turns out that there is, again, some linear algebra that comes to help us. So we can construct some matrix with variables with the following meaning. If the variable was set to 1, it would correspond to saying the qubit corresponding to the variable would be measured in Z basis. In X basis, and if the variable is set to 0, that would correspond to qubit being measured in Z basis. So because of that, we can construct one matrix that, based on valuation, captures all different possible measurements in terms of X and Z bases. And because of that, then the question, without too many details again, becomes that can we find some valuation resulting in a right invertible matrix in order to have polyflow? And how we can solve that? Well, so we now have a matrix with variables. And to answer whether this matrix ever, for some valuation, becomes right invertible is not easy. That's in general, it can't even be decided. But over a field F2, which this matrix is defined, this can be done. And the idea, without, again, why it works, is that we can just pick valuation at random and test it, whether the matrix is right invertible. We just have to move to some field extension of F2. The reason it works is briefly that each variable is in only one row, which means that characteristic polynomials of submatrices are multi-affine, and because of that, if they have root over F2, they will also have a root over some field extension of F2. And that means any field extension, and that's why we can move to field extension with the problem, in which if a non-root, so a valuation that gives rise to right invertible matrix exists, there must be a lot of them. And that's why just picking at random at some point is a good approach. But again, this method was maybe a bit boring in the sense that it only looks for poly X and Z measurements. Another thing that we were able to show is that we can always reverse the computation. So whenever we have a computation given as a labeled open graph that can be performed in deterministic way, one can ask, can we flip the inputs and outputs? So can we just consider the same computation but in the other direction? Can we also do that computation in a deterministic way? And it turns out that yes, we can. Using, again, some matrix formalism, we were able to show that if flow exists in one direction, it must exist in other direction. So that's possible. In the past, we only knew, again, how to do this for XY measurements. So being able to always say it's possible is quite useful. It has applications in ZX calculus, but again, not maybe a very valid thing to introduce now. And that brings me to the conclusions of this talk. So what we saw? Well, I explained that polyflow is a necessary and sufficient condition for robustly deterministic computation in MBQC model on labeled open graphs. The original definition of polyflow is hard to work with due to the number of different conditions one would have to verify. The way that I approach the question of can we make that set of conditions smaller was to use some linear algebra. So define some matrices and show that conditions for polyflow can be visualized by matrix multiplication and looking for inverse. That's the gist of this algebraic interpretation. And then I showed how we can use it to find flow in a more efficient way. I only explained one case where we have equal number of inputs and outputs. We were able to do it if we don't have that restriction. We just then have a problem that there is a lot of right inverses, but maybe that's not the most interesting thing to cover. But we were able to use this algebraic interpretation in many different ways to expand our knowledge about polyflow as notion for determinism. And some further further work ideas are, well, can we do something similar for other versions of MBQC? So I only considered here MBQC done on graph states. People are, for example, now considering MBQC on hypergraph states. So on hypergraphs, the byproducts that one can get due to the undesired measurement can be multi-qubit byproducts. So the question there is a lot more difficult. So we don't really have a flow structure that would precisely correspond to the determinism, but some work is being done. So maybe we can try to apply our just matrix way of looking at things there. Other notions also are on, instead of about qubits, graph states on qubits, we can consider graph states on qubits, where again the question is more challenging. Also, I showed you that we can look for poly X and Z measurement labeling that result in polyflow, but maybe we can extend this to look for more interesting computation to fully answer what type of computation, deterministic computation, one can perform on a given open graph. And finally, two most important questions is, can we improve circuit optimization procedures? So that, for example, T-count reduction, and can we speed up circuit extraction? The way those methods work, again, that overview is that we would start with some circuit, we would translate it to ZX calculus, for example, in a way that gives us something with flow. Then we would apply transformations that preserve flow. So that's where the flow again pops up. And this is done because in the end, we want to get a simplified circuit that still has flow. So a diagram with flow. And that's necessary for circuit extraction to get back to a circuit, right? So polyflow is there necessary at each step just because we wouldn't be able to do efficient circuit extraction in the end. We just don't know how to do it without flow. So perhaps our work could help with circuit extraction from ZX calculus and optimization that way. Okay, and that brings me to the end of the talk. So thank you.